Welcome back, everybody.
Welcome.
We are now episode 4, Robert, Feeding the Feeder, part 2. So last week, which we'll cover here in a recap, last week we kind of covered, the getting that powder into the inlet, controlling head pressure. We're going to carry forward with that, but wanted to mention before I hand it off to Robert, who's going to go over our 5 points, key manufacturing issues. We just got back from the Compaction Simulation Forum, and it was a great event, great science covered, really intriguing information. The agenda is still up for those who are interested to kind of go check out what it was about. There was quite a bit of new technology and new science being worked on throughout the industry, which was quite impressive to see.
So, Lisbon, Portugal too.
The scenery was amazing. Some of the
beautiful.
They're just killer. They're just gorgeous.
Yeah. So welcome back. I'm Robert Sedlock. This is Michael Ruck. We're your host here for Dr. TaBlitz. If you're just joining us, this is a educational podcast where we focus on tablet manufacturing issues and common issues like picking, sticking, capping, delamination, segregation, flow issues, all your major compression issues that you see in manufacturing. And what we're seeing on screen here are the 5 common reasons for having these issues. So number 1 is a formulation problem. If you look back on episode number 3, I ran a formulation that had MCC that with a very low bulk density of like 0.15 grams per ml. It was a small particle size grade MCC and dicalcium phosphate with magnesium stearate. And if you know dicalcium phosphate, it's very, very dense, like 0.85 grams per ml, larger particles. So a formulation problem having those density differences and particle size issues causes flow issues, compression problems, and so on. So that's number 1. Number 2 is environmental controls and conditions. So making sure the humidity is within spec, temperature is within reason. Number 3 is operator training. Your operators must know how to run the equipment properly, setting it up properly. Number 4 is process engineering. If you're granulating or you're milling, are you milling properly? Are you granulating properly? We're going to talk more about granulation in future episodes. But the last one here is the equipment conditions and design. Now we're talking about the hopper design, the feeder design, the paddles. So we're feeding the feeder. This is part number 2. Getting the powder from the hopper into the die is one of the most critical steps in the process. So if you have any equipment design issues or damage, that could be one of your root causes. So that's where we left off. Let's bring in Randy Young from Natoli Engineering, and let's continue our discussions on feeding the feeder. Welcome, Randy.
Yeah, welcome everybody. Hope you came back, and if we have any new viewers, we appreciate you joining. This is kind of where we left off, and you can see where the cursor is right now. That's the inlet to the actual feeder. So it comes down the hopper, it goes through the valve, and it goes into that inlet. And that inlet really controls the amount of flow that you get into the feeder. Balancing that flow in your feeder is very important. You can have too much powder in the feeder and you can have too little. How a powder flows is very critical. If you look at these 2 illustrations here, you can see this on the left, you'll see that small opening. If you have a powder that flows very well, that's not a big deal. It'll flow right through there. You won't have any issues. If you have a powder that flows very poorly, then the one on the right, it's going to flow very well through there because it's a much bigger opening with very little restriction. The other side of this coin is, what if I have a machine that has the opening on the right, but I have a powder that flows really well? That can be just as big of a problem as one that doesn't flow as well. We design machines around powders that don't flow very well, so everybody understands, because we see a lot of that in the industry.
Oh, yeah.
And we're building machines for the masses, right? But then we get into how do we optimize them and customize them. So what you see here on this slide, you can see this was a real customer application. We went on site with them, and they had the feeder opening on the left. You can see it's a very big opening. It's massive when you see it in person. So they have a powder that just flows phenomenally. It flows like water. It's just great. And what happened was they were making good tablets, but the machine was hard to control, okay? They were getting a lot of powder recirculation. They were getting a lot of powder into the feeder, so they were having to speed the paddles up. And paddle speed does 2 things. You get the raw speed, so maybe it helps spill the dye, maybe it doesn't. But faster speed gives you more torque. If I have a lot of powder in the feeder, sometimes people speed it up to get that torque. They don't really need the speed, but they need the torque. And then that's how they end up over mixing and getting segregation. So in this application, we went in and we 3D printed an opening that is significantly smaller, that little half moon shape you see. And we installed that. And that completely changed how this massive machine ran. They were running this machine at about 1,600 millimeters per second, about 55 RPMs on a 600 millimeter turret. So you can imagine the velocities that we were running at. And when we slowed the powder down going into that feeder, we were able to slow the paddles down because now we didn't have the mass in there. And then we got less recirculation in the recirculation band. We reduced that by almost 80%.
Now, Randy, if I recall correctly, when I heard this initially, you were actually not controlling the amount of flow with your head pressure valve enough, and this is something in addition you had to do. Right. Remember, if I understand that correctly?
Yep. Like I said, I know people don't understand it all the time, but great flowing powder can be just as big, if not a bigger problem, when you start looking at how do I reduce waste. And if I have a really good powder, it flows really well, it's very compressible, my expectation for tablet consistency goes way up in most cases. So to achieve that, sometimes we have to optimize these machines to achieve those goals, because like this particular application, the customer was running 128 milligram tablet.
Okay.
It's very small. It needs very little powder.
Right.
So you have an opening that's this big. How do you hold the powder back? But when I make that opening this big, just a natural flow of the powder, now it's slowed down just by the aperture. And then when I take less powder out of the feeder, now I'm not actually having powder leaking out, getting into the recirculation band, because powder has nowhere to go. It keeps filling up, and it has nowhere to go. So it finds its way out of the feeder into the recirculation band. So by reducing that, we dropped the RSDs on this machine dramatically, and it became the machine was almost easy to operate. We put the recipe in, we hit start, and the machine just ran, and it ran for hours like that.
So just to recap for everybody, so we're talking about this inlet here. And remember last episode, we talked about controlling the head pressure with this valve system. This valve system is actually feeding this new 3D printed inlet, which is here. Right, so this tube right here would actually go into the top of this inlet, and then this inlet, this 3D printed inlet, would go sit on top of the feeder pan here. Yeah, and those are two steps that is being used to help control the powder flow, and that's what Randy's explaining here.
Yeah, Mike. Just so you know, in that because we work with a lot of different companies, and this is one style of machine. You can see this inlet is different than the one I showed you. That machine, that inlet that we 3D printed, that was on a machine that ran a standard hopper.
Okay.
It didn't really require would the valve have helped? Not really, because I still had an opening that's this big. But I did want to bring up that you don't have to have this complex fill system above it always to remediate issues. There's other ways to do it. And I can tell you we do studies, right? And we look at compaction studies, and then sometimes we start looking at flow. How does it flow? What are the micromeritics? And knowing that up front allows me to pick the right machine for this product. If I have a large diameter opening and a very large turret and have a powder that flows like water, maybe that's not the best choice. And that's what these exercises tell us that we go through with the customers.
Brilliant.
All right.
So here now we look at paddles, and paddles come in all different designs. You can see here's a very large, here's a plow design. They come in different sizes, right, for your machine, and then they come in all different designs. So what happens is you have the paddles in your machine, and I'm going to talk about what happens with these paddles. So what they do is they're in your machine and they begin to turn, and then what happens is the powder's flowing over the top of them. So you can see this paddle I have here is a very tall paddle. So I'm aerating the powder, I'm lifting it up, and then it's coming down. I'm lifting it up and it's coming down. And this paddle is also very big, very large, right? So if I have a paddle, look at this paddle, it's little.
Yeah.
This might be on your R&D machine or a smaller machine that somebody might have. The velocity this paddle is spinning at is significantly different than this one. It's almost double. So when this one's spinning at 50, this one has to spin at 100 to be at the same velocity.
Well, and key things, you're measuring velocity at the tip of the paddle, right?
Right. We go from the center of the die to the center of the paddle, the center of the paddle where you can see it in here right now, where this hole is.
Okay.
Yeah.
Anyway, same thing you do on a turret. You go from the center of the die to the center of the turret. It's identically the same. And we found that this has a big impact on the powder once it's in the feeder. Because now if I have these large paddles and they're very big and I'm spinning them at high rates of speed, I'm moving powder in the die bore, but I'm also moving it to the sides. So you can see in this design that you see on the screen, you can imagine if I'm spinning these paddles at a very high rate of speed, I'm pushing powder against the outside walls of that feeder.
Right.
So I can go to a smaller paddle, right? In terms of design, a small round. So now I don't have this up and down motion. I'm not aerating the powder. I'm not moving it very much. I'm just gradually moving it into the die. It's a very relaxed environment. The powder responds much better in many cases. And again, if you have a powder that doesn't flow well, I might need this big plow design. If I have a powder that flows really well, I might need this little wire design.
Yeah, and for those of you who are trying to understand what the plow design is, what Randy's explaining here, you'll see there's a chamfer on the edge of this paddle. It's hard to see here, but well, maybe if I hide the body here, you'll see here that this paddle actually has a chamfer on it, and it spins clockwise the way we're looking at it here, and so it's actually pushing the powder into the die. That's what we're calling the plow design. And then this one here is the wire. And the other one that we had shown was just the standard. So that's what we're saying here for the plow design.
Yeah, and they can be mixed. People mix them because one of them is a metering paddle and one of them is a fill paddle, basically. So you're metering the amount of powder coming into the feeder, and then you're also moving that powder from its metering position into the actual fill side of the paddles. If you spin that up, Mike, there's also another really important aspect of powder and feeding, and that you can see that inserts that is there. So you can see that insert is, you have a very large insert, but you have a very small opening, and that's pretty common. Like here, you can see this is one where you can see it's a very large opening, and then you have them where they're very small openings. And what we found through our studies is if we match these openings to the size of the tablet that we're running, we get much better results in terms of tablet consistency, especially on smaller tablets where a 5% variation is only a few milligrams. Because you can imagine if I have this very large opening and then I have this very small tip, I have all this powder that's sitting on the die table. All that powder sitting on the die table, you can imagine. My die table is spinning at 1,600 millimeters per second. The powder is going to pick up the velocity of that die table, and it's going to be moved to one side of the feeder at 1,600 millimeters per second, and it's going to be pushed against it.
Densified.
Against it.
Yeah, densified.
If it can't get out, right, it's going to start to densify. Powder that comes around in your recirculation band re-enters the feeder, goes through the metering paddle, passes over to the delivery paddle. It becomes to get densified again. And if I have big tablets, 2 grams, you don't see as big of an impact of this. When I have small tablets, 300 milligrams and below, 400 milligrams and below, this densification of the powder actually causes your RSDs to fluctuate quite a bit. You look at your tools and you say, my working lengths are really good. Everything seems to be great. Why am I getting this? And there's another slide. You can bring it up, Mike.
Yeah. I just want to highlight what you're talking about. It's actually displayed here. So this is the original feeder pan, right, for this design. And here's the die. And then here is it. It's, pushing that powder into the die. Whereas changing that aperture opening, right, to be basically a little bit bigger than the die bore opening is what this is intended to do, to prevent how much powder you're moving across the tray.
Yeah. And we just so you know, we see about between 30 and a 40% difference seems to be the sweet spot compared to the diameter of the tablet. And you can see they're in all different sizes. They're in all different materials. If you have a powder that flows really well, you might choose a material that's a little bit softer. It may not be aluminum bronze. You may want like a PEEK material, so I can really push that insert down on the die table to trap that powder in there. I don't want to get any leaking out. I want to have as little recirculation as I can. And then you want to match this opening to the size of your tablet. And I think we have a slide for that, don't we, Mike?
I don't know if I have a slide for that one.
Because we actually had where it was good, where we showed 3 different options. Anyway.
I don't think we have a slide for that one.
Yeah, well, what we try to do is we try to match the materials so we can get a good seal on that die table so we don't have any powder escaping. And then we try to match the diameter of the tablet or the size. If I'm running, here's a real good example. And I don't know if you guys can see this really well, but you can imagine if this is my opening and then this is my tablet, look at how big that tablet is. That's not going to work very well. But
put that up there again, Randy. That way it's a little bit bigger for people to kind of see.
If I go here, there.
There you go. Yeah, there you go.
So you can see, look how close it is. But now if I go to this one, right?
Yeah.
See?
Massive difference.
So these would match very well together. If I were running this tablet, I would choose this one. And matching this is very important, especially when we're looking at trying to achieve the most consistent tablets we can for dosing. There's another slide, Mike, I think, if you can go to it. Yeah, right here you can see. So what we did, and when we did these studies, we looked at how the powder densified inside the feeder when we did this. And this was a very compressible material. So you can see all the powder. Look how densified it got on the left side, which this turret turned clockwise. So it was denser on the left side than it was on the right side. On the left side is where it's delivered to the dies. So you can imagine as this densified material starts breaking off, it ends up in the die, and now you have weight fluctuation because the material is denser now than it is on the left-hand side than it was when it went into the machine through the hopper. It's now denser.
Randy, you bring up a good point. One thing I wanted to mention was the micromeretics of your formula. We test the micromeretics, right? Which is the bulk density, tap density, particle size distribution, moisture, things like that. But it'd be interesting to take a sample of that powder we're looking at and test the micromeretics on that now, which is probably different from the original starting powder, right? So depending on what feeder insert you're using, you could be changing your powder micromeretics, and you have the data for it, but when it's actually going into the die, it's different because you're using the wrong feeder insert. So that's interesting.
And
that's a good point too, Robert. I mean, because people are assuming, okay, well, I went through my blending process, now I'm going to go into the hopper, right? But technically, you're not done blending yet. Your paddles are going to continue to blend this based upon how your setup is. So you're densifying and blending it in the machine.
Yeah, and there's another side of this too, and this comes back to micromeretics is very important. When we work with customers, we look at 2 things. We look at what is the compactability. We do a compaction study, and I think that's part of micromeretics, isn't it?
USP 1062 profiling, which it's a service that we do offer customers. We look at that and the micromeretics combined.
Yeah. So now if I look at those compaction studies, Robert, and I see that I have a very compactable material at very low forces, right? I can compress this at 5 kilonewtons, and I get a really robust tablet. That tells me that's a very compressible material. So the more I try to densify that material as it moves across the die table and it moves against the feeder, I'm beginning to get those molecules to start to react, almost like if you had pre-compression set too high.
Yeah.
You start to densify the material. In this case, I'm doing it before I put it in the die, and that's why it affects weight. In the other case, it can affect hardness just by the molecules don't react the same way. But in this case, I'm literally affecting weight because that denser material is now in the die. and it's not consistently in every die the same.
Right. And the effect of pre-compression is when your particles are closer together, you got more contact surface area for better bonding points. So the particles are bonding better when they're closer together. That's what you're explaining there. Yes.
Yeah. And it doesn't take much, as you see with pre-compression. It doesn't take much to densify that material, where when you walk it around and you push it out, it made a tablet. Now you can't necessarily pick it up, but it stayed in the tablet shape. Right. So that material was being bonded right there, and that's what's happening in your feeder. And you can control this with the insert, with the paddles, with the paddle speed. Do you have it sealed against the die table? But the second I know everything I can about this powder, so we know the compactability, we've studied that. Now Robert tells us all about this material, and he gives us the flow properties. So now we know this is a high flowing material that is very compactable. So now I know what to do when I start choosing my machine in production. I know what to do when I start setting up my machine. What insert do I choose? What paddle do I choose? And then I install those into the machine. And these are all things that we can do with people. It's not that we have to redesign your whole machine. We're just changing small aspects of your machine that were really meant to be changed from the beginning.
Yeah, let me bring up a good point, though. A lot of times we're on the phone trying to fix manufacturing problems, and we can't change the formulation. They don't want to change the process, but these tools that you're bringing up, Randy, these are the solutions that can be very useful for manufacturing guys. But you bring up a good point. This should be studied in R&D as well, so we understand in R&D how we're going to scale this up and what type of setup we're going to have when we scale up. So yeah, no, I appreciate all this.
Yeah, because we've gone into plants and we've worked with them, and they're trying to run a product and they're just not getting the result they want for whatever reason. And most of the time it's weight control. They want to hold very tight weight control for dosing on these small tablets. And sometimes we just switch machines. A machine that runs the same tooling, the machine just has a different design about it. It has a smaller opening. It has insert technology that we can take advantage of. You have round paddles for it. And all of a sudden, it just like it didn't have any issues at all. And all we did was change machines. But we changed the physical properties of that machine. So that's some things that we work with people on all the time, because like Robert said, a lot of times when I get involved, I get moved into this through our tooling group. And then I'm dealing with a customer who says we can't change our formulation. Right. So that's where we learn these things. But the reality is we're building R&D machines that allow you to study all of this stuff, so you know it way upstream before you ever validate this product. You know all these characteristics before you do that. We have R&D machines that'll study paddle velocity, machine velocity, fill times, consolidation times. We can study this consolidation in the feeder in an R&D environment or on an R&D machine.
That's something important, I think, to Randy, to make sure we mention to the audience. It doesn't have to be a specific machine. You can optimize. You have equipment you've already invested in. If you need to optimize it, these tools, techniques, and approaches that Randy's presenting here, these can be done on any piece of equipment with some
all these
slight
customization. Were from 4 different engagements we had with customers.
Perfect. So
they weren't just like all one. They were just 4 different engagements that we had with different customers, different machines, different powders, but the science was all the same. Yeah. And then this is where we get into, and this is another part of the science. So it's in, and you have your fill cam, and I'm sure Robert goes over fill cams at great lengths in his training. We do here in our training. If you have a fill cam and it's too large, so now if I have a 12 millimeter fill cam and the fill cam pulls down, I fill it with 12 millimeters, I move over to dosing, and then I push out 8 millimeters of that 12. So now I've pushed 8 millimeters back into the feeder. The paddles are spinning over it. The powder's coming up. The paddles are spinning over it. And now I'm pushing that against those moving paddles, and those paddles are moving it to the side of the feeder immediately. So if I have all that push out, now again, I start densifying the material. And so then you say, okay, now we're going to go to a 10 millimeter fill cam. And now I'm going to push out less, and we're going to go to 8. Okay, now I'm pushing out 4 and I'm keeping 4. But there's another way to look at this. And it's also how long do we have to fill that die? So on this illustration, you can see the dot on the one on the left, Mike. On the left.
Yeah.
There. That's where you're dosing. That's where the punch is moved onto the dosing head. and it's starting its vertical movement. That is the end of fill, because now we're pushing out. Fill is done. You see 2 circles on the right. So you see the circle. That's where this particular machine, that's where its standard position was. It filled from those 2 dots, the one on the right and the one on the left. And that was its fill stream. And they still weren't getting the weights they wanted. So we redesigned the fill cam so we pull down sooner and faster. So now I have a longer track to fill that die, and I've pulled down at a higher speed to
more
get
vacuum.
more natural vacuum to pull that powder down in the die. And this particular customer, we went from, and I know this sounds unusual, but they went from around 2 RSDs, but they wanted to be at 1. And these are tablet RSDs. And when we made this change with this fill cam, we got below 1.
Wow.
And they were between 2 and 3. And again, this is a real extreme case with a customer, but it is a fact that this wasn't good enough for them. So they wanted to be below 1. And we were able to achieve that by just redesigning a fill cam, giving them longer time to pull, longer with the fill cam, with the tool down, and faster pull down. And we were able to achieve the goals they wanted.
Yeah, and we're able to measure that in milliseconds as well. So now when you're doing scale up, you can compare your R&D press to manufacturing. Hey, Michael, I think we're almost out of time here.
We're almost out of time. We went a little late, guys, today, but I do want to give some time to the audience for some questions, because that's key and important here.
But yeah, Robert, when you do that study with the micromeretics and we start looking inside the feeder, we're more than happy to assist with that, because we do a lot of it with the customers all the time.
Yeah, well, that's going to be our next episode, by the way. We're going to talk about powder micromeretics, and all of this will impact the tableting process and these defects. So it's going to be a nice transition from Randy's talk. Now we're going to talk about powder properties. And this new study we're just talking about now is testing the micromeretics after the material's been in the feeder, densifying. All right, we got a question here, don't we?
No, we got a hello from Thurl Fisher. Hello.
Hey.
Hello, Canada. How's it going?
Oh,
Thanks for watching. Thanks for tuning in.
And yeah, we saw them in Portugal, right?
Yeah, absolutely.
Yeah.
So let's see. Great topic. Thanks for sharing your knowledge. Will this episode be available later on your YouTube channel? Yes, it will. So
absolutely.
Just so everybody knows, these are open and streamed live, but they always get published to our LinkedIn channel as well as our YouTube channel. So if you're a LinkedIn user, you go there, you can watch all of our history, or if you're a YouTube user, you could do the same. Our handle is at Dr. TaBlitz on YouTube, and then obviously our LinkedIn channel is Dr. TaBlitz, so / Dr. TaBlitz, and then you'll see all of our historical videos if you go to the events page.
Hey, Mike, if they send in questions after the fact,
good point.
Then how do they do that? Because like if somebody has a question, because we have statistics on many, many different machines. So if someone says, I have this machine, we have a lot of data that we can share with them to try to help them.
Yeah, perfect. So you go to dr.tablitzlabs.com. You can actually submit your request for information, or even schedule a help session, and we'll actually pull the people in to answer any questions you want. So if it's press technology we need to talk about, if it's formulation development we need to talk about, we'll have all kinds of people there available to help you solve your issues. So just go to dr.tablitzlabs.com, and that's where you could submit your request for information, or schedule a meeting with us to get help with your issues. So good point, Randy. We should mention that more.
Another point Randy mentioned is it's all machines out there. So we work with all your machines, Fetties, Korches, Manassi, Stokes, Synthegon. Don't matter what it is, we work with it. So, this is a good opportunity to fix some of your problems.
Yeah, and just so people know, we rebuild and we make parts for all these different machines. So that's where we gain a lot of this knowledge. And it's not just Natoli machines that we gain knowledge on, it's all of them. Right. So that's why we're able to be really a resource, because we don't care if it is a Fetty, a Korsch, a Killy, and a Manassi. We don't really care. A Stokes, we don't really care. We're just there to help them.
Yeah. Great. Yeah. Wow. I can't believe 30 minutes flew by this quick, guys.
It did. If there's any other questions, we've got about a minute left, but I want to make sure we kind of cover next episode. Just like Robert said, we're going to be covering micromeretics. We're going to be going through, we'll actually have some live lab demonstrations. We're actually going to be running the press, and we got some treats for you guys in there. And then we'll have a follow-up episode after that to go over the microfluidics that we produce from these powders. And it'll be kind of exciting to see how you guys respond and interact with. We're actually going to have live data to break down some of the things we're going to cause or correlate. And we'll show you how that data actually works for you or against you. So good stuff.
July 14th is a Tuesday. I think that's when we're planning our next one. So look on LinkedIn, look on your emails. You'll see the new date coming up here.
Yep, Microfluidics Part 1, July 14th. You'll see it on your YouTube or your LinkedIn statuses. So please like, subscribe, and follow, and we'll catch you next time.
Hey, Mike?
Yes.
Is there a way for us to send invites for these, if they wanted to see them live, to send invites to our customers? We obviously we have a lot of Tablet Press customers that they worked with us a lot on tooling and parts and machines and some of what I went over today, but the whole microfluidics side, they might not have as much knowledge. Is there a way to invite them to these podcasts live?
Yes, yeah. We can actually send you guys share links, and you can share it with your customers, and that way you can kind of get them aware of some of the new technologies that we'll continue to bring on.
That'd be great.
Yeah, absolutely. We'll get you set up, Randy, so you can share.
Yeah, thank you.
Yep, not a problem.
Thank you, Randy, for joining us.
Thanks for attending. Appreciate your time. Have a good one.
All right.
Thank you, everyone.
July 14th.